Here are the football shirts from our 7-a-side team. I've been asked to find the shirt with squad number 31 as it needs repairing. Now this is easy to do for just 7 shirts, just check each one until I find it. But what if I had a club squad and loads of shirts to check? Here's where thinking in terms of algorithms might help. Let's consider the most natural method of searching for the shirt. You start at the first one on the left and look at each one, read the squad number and compare it with the number we're looking for. Do that until we find it, or we looked at all of the shirts and not found it. Now of course we're assuming that each shirt has a unique number, otherwise we'd have to check the full set each time. We could have equally started at the shirt on the right and worked leftwards as well. This simple solution probably doesn't warrant documenting the steps, but let's do it anyway. Let's show the algorithm in the form of a flowchart and record the result of each step using a trace table. As always, we begin with the terminator, the start. There are 2 inputs to the algorithm, the number of the shirt we want to find and the shirts themselves. Rather than being specific about numbers and shirts, we'll use an abstraction and just call the shirt number the item to search for, and the shirts the list of items to be searched. We show these as input symbols. Next, we have our first task, which is to go to the first shirt and look at the number, or in abstract terms, go to the first item in the list. Comparing the item, shirt number 3, with the search item, shirt 31, we ask ourselves if they are the same. If they are, we found what we are looking for, and if not, we move to the next item in the list. But before we do, we add a check to see if we're at the end of the list, and if we are, then we've not found what we were looking for. Now let's test our algorithm by running through the flowchart, recording results in a trace table, and turning the shirts as we go. Here's the empty trace table. In it I'm recording the search item, the list of numbers the shirts have, what the current item is, and what the result of the algorithm is. In the real world, of course, we won't know what the list of shirt numbers are until we turn them over, but for testing purposes this is okay. Let's run through the steps in our algorithm. First, record the item to be searched for and the shirt numbers in the table. 31 is what we're searching for, and these are the numbers on the 7 shirts. Look at the first item. Is it number 31? No, it's shirt 3. Are we at the end of the list? No, so go to the next item. Keep repeating until we have a result. Shirts 42, 87 and 31. This is what we're searching for, so record the result as item found and end. It looks as though our algorithm works okay, but really we should test it for the case when the thing we're searching for is not present. But I'll leave that up to you. Now, this algorithm is called a linear or sequential search, as it involves going through each item in turn in a linear fashion. It's fine for a small number of items, but inefficient for a large number, as you may have to look at every item before finding the one you want. It's probably struck you that the reason a linear search is necessary in this case is that the shirts are not in any particular order. But something interesting happens when we do put the shirts in order. We can see that it makes it possible to guess approximately where the item we are searching for could be, and this leads us to our next search algorithm. Let's assume that the shirts have been put in order, lowest number on the left, highest on the right. We don't know what the numbers are until we actually choose one. The basic algorithm works as follows. First, choose the midpoint shirt from the group of shirts. Then, if this shirt is numbered less than the one we want, we discard this shirt and all of the others to the left of it. This is because we know that these are all numbered less than the one we are looking for. If it's numbered higher, we discard everything to the right. We then repeat this, choosing the midpoint and discarding until we find what we are searching for. Let's write this algorithm as a flowchart, try it out, and use a trace table to record the steps. Before, we have the start terminator and the 2 inputs to the algorithm, the list of items and the item to search for. The first step is to select the midpoint item from the list. Next we check if the item we selected is the same as what we're searching for. If it is, then the item's been found and we end. If not, we ask if the search item is less than the item we've selected. If it is, then we discard all of the list items after and including the midpoint item. If it's greater, then we discard the items before and including the midpoint item. If there are no items left to check, then the item we're searching for is not there. Otherwise, we select the midpoint item from the remaining items and repeat the whole process. Now let's step through the algorithm using the football shirts as an example. In the trace table, we're going to record the input data, which is the number to search for, and the list of shirt numbers to search through. I'll put these inside square brackets to show them clearer. We'll also record the midpoint item, which is the shirt we've picked, and the result of the algorithm, which is item found or not. The first thing in the flowchart is recording the two inputs, so we put these in the trace table, 31 for the search item and the list of shirt numbers. Of course, in real life, we don't know what the shirt numbers are, but for test purposes, let's assume we do. Selecting the midpoint shirt reveals that it is number 25, so it's not what we are looking for. As 31 is greater than 25, the step to take is to discard the items before and including what we've selected. We're now left with shirts 31, 42 and 87, so we record that. We still have some items to search through, so we repeat and choose the midpoint, revealing that it's shirt 42. Again, it's not what we are looking for, and as 31 is less than 42, we discard everything after and including 42. We then repeat again. This time the last item is what we're searching for, so record that the item is found and end. It seems to work okay. The algorithm we've just looked at is called the binary search, with binary meaning cutting the list in half. It's taken 3 steps to find out what we were searching for, which for a small number of items isn't much different to the linear search. However, if we had 1,000 items to search, binary search would take a maximum of only 10 steps, much faster than checking every one potentially. We can therefore say that binary search is more efficient than linear search. Of course, the list of items has to be sorted in order for binary search to work, and it's to sorting algorithms that we now turn. We're going to look at 3 different algorithms for sorting: the insertion sort, the bubble sort and the merge sort. All of them achieve the same thing, but do so differently and with different efficiencies. Here's the flowchart of the insertion sort algorithm. The algorithm works in the same way we sort playing cards in our hands. That is, we pick a card and find out where to reinsert it into the pack by placing it before a higher value card. We'll run through the algorithm using our football shirts and record some information in a trace table as usual to check that the algorithm works. We'll record the position in the list, the item at that position, the insertion point, which I'm going to call IPOS, and the contents of the list after insertion. Note that we're using the convention that the first item in the list is called item 0 rather than 1, so that the end position is actually 6. Looking at the flowchart, we see the start and the input of the unsorted list of items. We start at the second shirt, number 25, and as we're not at the end of the shirts, we compare this to the previous shirts, noting the point where it is less than one shirt but greater than the one before. I'll call that point the insertion point, or IPOS, as in the flowchart. For number 25, the insertion point is before the first item, which is position 0. The insertion point has been found, so we remove shirt 25, shift all of the shirts to the left of the insertion point along by 1, and then insert it into position. We then move our position to the next shirt, 42, and repeat the process. This time though, we don't find an insertion point, so we simply move to the next position. You get the idea, so let's complete the run and record the results in a trace table. All done, and the shirts are sorted, so it looks like our algorithm works okay. There's been a lot of checking and moving items around with the insertion sort, so let's look at an alternative, the bubble sort. Here's a flowchart representing the bubble sort. The basic idea behind the bubble sort is to repeatedly go through a list, swapping adjacent items if they are in the wrong order. Let's go through it using our football shirts as an example. I've also set up a trace table as usual to show what's happening. In it we'll record the list as it changes and what gets swapped. Okay, let's step through the flowchart. After the start symbol we have this list of shirts which are in no particular order. We record this in the trace table. Now we set the end position to the end of the list and the start position to the start. I'm using 0 as the first item again. We do a quick check to make sure that we're not at the end of the list, as this is how we'll exit from each loop. Using the start position, we compare the shirt in this position, which is 31, with the next shirt, 25, to see if it's greater. It is, so we swap them, not forgetting to update our trace table at the same time. Moving on to the next position, which is now shirt 31, we compare this with the next one, shirt 42. This isn't greater, so we don't swap. Moving on again, the next shirt is 42, which is greater than the next, 3, so we swap. We repeat this process until we reach the end of the shirts. Let's record the list of numbers in the trace table. As you can see, the result of this swapping is that the highest number shirt, 87, has been sorted to the end. It's not necessary to include this shirt again, so we move our end position in by 1. Moving the start position to the first shirt again, 25, we repeat the process again, this time swapping 31 and 3, 31 and 8, as well as 42 and 12, which leaves 42 as the sorted shirt. And so it goes on until we haven't anything left to swap, at which point everything has been sorted. Well, that's the bubble sort. In terms of efficiency, both the insertion sort and bubble sort are pretty much equivalent. They work well when we have a low number, say in the tens, to sort. Our next sorting algorithm, the merge sort, is a lot quicker for a large number of items, but is also more difficult to understand, so let's take a look at it. Here is the flowchart and trace table for the merge sort. The merge sort is a type of divide and conquer algorithm. A divide and conquer algorithm is one that repeatedly breaks down a problem into many sub-problems, solves each problem directly, and then combines these solutions to solve the original problem. The merge sort works by dividing an unsorted list into a number of sublists, each containing one element. It then merges these sublists to produce new sorted sublists until there is only one list remaining. The key thing about this is that the algorithm shown here is recursive, which means that it uses itself over and over again, but with only parts of its original data. This recursiveness is shown as the merge sort defined process. It sounds complicated, but it'll become clear as we go through it. Let's work through the steps using the football shirts as an example, and recording the results in a trace table as usual. The results I want to record are the list as it gets split into left and right sides, and the merged list. Since this algorithm uses itself recursively, I'm also showing something to indicate what level we're at. This will become clearer as we run the algorithm. The first thing is that we check if the supplied list has more than one item and end if it doesn't. Next, we find the midpoint of the list, here it's 3, and divide into two parts, left and right. The left side has shirts 31, 25 and 42, and the right side has the other shirts. We then run this algorithm again using the left side of the list. We're now 2 levels down if you like, and the input to the algorithm is shirts 31, 25 and 42. When we go back up a level, we'll see the original right side again. We find the midpoint, here it's position 1, and split into left and right parts again. Shirt 31 is in the left side, with shirts 25 and 42 in the right. Down again another level, but this time with just shirt 31. Since we only have one item, we come back up a level. Now we do it again, but this time with the right side, which gets split into the individual items 25 and 42. Okay, we're at this point in the flowchart and are using 25 as the only item in the left list, and 42 is the only item in the right list. The final step in the flowchart is to insert these items in order into the list at this level. We have a left list of 25 and a right of 42, which are ordered and put into the list to give 25 and 42. Of course, they're already in order, so we don't actually do anything. We now end this level and go back up to the previous level, where we now have a left list containing 31 and a right list of 25 and 42. We put these in order to give 25, 31 and 42. We then end and go back to level 1. So we've done the left side of the original list. Now the right side of the list has numbers 3, 8, 87 and 12. Repeating the whole process splits the lists into 3 and 8 and 87 and 12 at the next level and the individual numbers thereafter. On the way back up, these get sorted into 3, 8 and 12, 87, and finally for the right side to 3, 8, 12 and 87. In the final step, at the top level, we take the two sorted left and right lists and put them in order. Since both halves are already in order, it's easy and quick to do the final sort. That's it. Whilst the merge sort is more complicated than the bubble or insertion sort, it is considerably faster, especially when dealing with a large number of items. Well, there we have it, an introduction to searching and sorting algorithms. We've looked at simple linear searching, which is used when things are not sorted, and the binary search when things are. Efficient searching requires that things are sorted, and to do that we need sorting algorithms. From the ones we've looked at, the merge sort is the fastest when a large number of items need to be sorted, but the insertion and bubble sorts work well when there are just a few. So which searching algorithm you use depends on what the data is you're trying to sort. In some instances, the simple algorithms work best. There are more searching and sorting algorithms out there, so do check them out if you are interested in learning more.